Hello and welcome back. We are studying the interpolation by Lagrange polynomials. The method that is given is the method of Lagrange, and we are studying interpolation of functions by these polynomials. Today we are going to see some examples of this method, and we will also see if there is an error and whether we can write down the error explicitly. All right, so just let's recall what we mean by this Lagrange interpolation. Whenever you have distinct n plus 1 points, it is important that these n plus 1 points be distinct. So whenever you have these distinct points and their values are specified, so f of x naught is y naught, f of x1 is y1, f of x2 is y2, dot dot dot, f of xn is yn, yi need not be distinct, but xi's have to be distinct. So whenever you have such a data, then Lagrange's method gives you a polynomial whose degree is at most n with the property that f of xi is pxi. So there is a polynomial of degree at most n which has the property that at xi the polynomial value is yi. This is what Lagrange says. How do we construct this polynomial? This polynomial is constructed in this way. It is first of all we solve for some special problems which is given by at each xi we have the value to be 1 and other xj's the value is 0. That gives you a polynomial which we call Li. These are the Lagrange polynomials to the given set of n plus 1 points, and then you simply have to take their sum, summation yi Li, or y naught L naught plus y1 L1 dot 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 yn Ln. This is what we have to do. Here these Li are also defined. We have written down the explicit formula for Li. You know, Li has to be 0 for each xj other than I. So Li has to be a multiple of these x minus x naught, x minus x1 up to x minus xi minus 1, x minus xi plus 1 up to x minus xn. We have removed the x minus xi because at xi it has to take the value 1. So it has to be 0 at all these other polynomials, and then at xi it should take the value 1. So we just see what would happen if you put x equal to xi in the numerator and divide by that particular term. This is the very simple method. Meaning once you think about it, one realizes that it is indeed a simple method, and let's do some examples to this. So we had done this, we actually did a general example of a constant polynomial already. So where we have been given only 1 point and some particular value at that point, and we saw that for one single point, the function that we get is a constant function. Let's now look at the 2 points. So f of 2 is 4 and f of 5 is 1. And we want to find the polynomial p which interpolates the function f at these 2 points. Okay. So here x naught is 2, y naught is 4. Y naught is the value of the function at x naught. X1 is 5 and its value which is y1 which is 1. So we can write down L naught. Now L naught has to be 0 at x1 and it should be 1 at x naught. So since it is 0 at x1 which is 5, it should be a multiple of x minus 5. And then because the value at x naught which is 2, it should be 1. We just make sure that the multiple is adjusted so that the value of L naught is 1 at x naught which is 2. Okay. So we see that x minus 5 upon 3 with a negative sign, or 5 minus x upon 3. So if you put x equal to 5, you get 0, and x equal to 2 will give you 1. Similarly, you can compute L1 which turns out to be 1/3 x minus 2. And now we know how to compute the Lagrange polynomial. You have to take this 1/3 x minus 5 with a negative sign, multiply to that by y naught. So you get minus 4 by 3 into x minus 5. And then you take the L1 and multiply to that by the value y1 which happens to be 1. So you just put L1 there. And sorting it out, simplifying it, will give you the polynomial to be minus x plus 6. It's a linear polynomial. We are working with 2 points and we get a linear polynomial. When you worked with a single point, you got the constant polynomial. So the degree of the polynomial is at most the number of points minus 1. That is okay. Maybe when we were working with n plus 1 points, we said that our polynomial will have degree at most n. You can check easily that minus x plus 6 or 6 minus x, that's the line which passes through the point 2 comma 4 and 5 comma 1. It's the line which goes down because the slope is negative. It goes down, and at 2 the value is 4, at 5 the value is 1, and then it will intersect the x-axis at x equal to 6. It intersects the y-axis where x is 0, that's where y will intersect, but the y value is now 6, and that's how this polynomial, this straight line goes. It is parallel to y equal to minus 6. Okay, so let's go to one more example. We will look at these 3 points: x0 equal to 2, x1 equal to 2.75, and x2 equal to 4. These are the nodes. So these xi's, we call them points or input values. They are also called nodes. So we have these 3 nodes, and what is the function that we would like to interpolate at these 3 nodes? It's the function 1 upon x, which we have worked with earlier using the Taylor polynomial. Here we want to find a polynomial interpolating the function at these 3 points. So of course, we need to first determine the polynomials L0, L1, L2. These polynomials, once again, remember, these polynomials do not depend on the function. They depend only on the nodes because they are given with the x0, x1 and x2. Those are the 3 nodes that we need to define these polynomials. So L0 is something which has to be 0 on x1 and x2, but it should take value 1 on x0. So it will be x minus 2.75 into x minus 4 upon something, and ultimately the answer is 2 by 3 into the product of these polynomials. This is a quadratic polynomial L0. Similarly, L1 is a quadratic polynomial and L2 is a quadratic polynomial. So we have 3 degree 2 polynomials, and finally we can write down the value of the Lagrange polynomial Px interpolating 1 upon x at these 3 points, 2, 2.75 and 4. And the polynomial happens to be 1 by 22x square minus 35 by 88x plus 49 upon 44. So it's a slightly complicated polynomial. The Lagrange polynomial, the Taylor polynomial, if you remember, was very easy. And the Taylor polynomial did not approximate your function well at all. But this polynomial does approximate your function quite well. Here we had 3 points, and so naturally the polynomial will have degree less than or equal to 2. In this case, it happens to be of the degree 2. What is the value of this polynomial at x equal to 3? It is this polynomial 1 by 22x squared minus 35 by 88x plus 49 by 44. And we want to compute the value of this polynomial at x equal to 3. So if you put the values down, you see that it turns out to be 0.3295454545454. 54 will continue, but if you want to cut it at some stage, then that 4, because the next one is 5, will become 5, and so you get 0.32955. This is very close to 1/3. Remember, the function is 1 upon x, and we are computing the value at x equal to 3. So we should get 1/3, which is 0.3333. This is very close to that. So the polynomial is very good. And it is no surprise, of course, because you have interpolated the polynomial at an interval which contains 3. And so therefore, on the interval, you will expect that the polynomial will give you a nice approximation to the function. Okay, and also we did not take the values to be 2, 3 and 4, but we took it to be 2, 2.75 and 4. So that we can compute the value of the resulting interpolating polynomial at 3 and see how better it is than the Taylor polynomial. We can actually also plot the graph. We will see the graph of fx, which is 1 upon x, that's the hyperbola, and we will see how this polynomial behaves with that. This is a quadratic polynomial, so it's some sort of a parabola. So this is how we have this blue graph, which is 1 upon x. It starts from infinity and it goes down to 0 as x goes to infinity. But this parabola, remember parabola, both the values have to go up, and it does indeed go up. It starts from positive infinity, long before in the second quadrant, and then it comes close. It will, of course, hit the values at x equal to 2 at 2.75 and also at at x equal to 4. Okay, so it hits all these values. It is very close to the function that we are working with, and then it will again go up ultimately because it's a parabola, so it has to go up. This is how the Lagrange polynomial, although it's a polynomial of degree 3, but we see that it is not just working very well with respect to 2 and 4, but even beyond 4 for some time and even before 2 for some time. So there is a very nice behavior of the interpolating polynomial that we see here. Let's see one more example. This is a very interesting example. I am taking the value at 1 equal to 1 and the value at 2 also equal to 1. If I were looking only at f of 1 equal to 1, then there would be the constant polynomial that we would get. Here I have one more node, x equal to 2, but I am taking the value to be 1. What would be the polynomial for such a data? Let's compute Lagrange polynomials. Our nodes are 1 and 2. Lagrange polynomial will not see where the values are. They just look at the nodes. The nodes will give you Lagrange polynomials to be L0, which is minus of x minus 2, and L1, which is x minus 1. These are two degree 1 Lagrange polynomials. The Lagrange polynomials for n plus 1 nodes are always degree n polynomials. There is no doubt about the degree being smaller possibly than n. They always have degree n. Whenever you have n plus 1 distinct nodes, the Lagrange polynomials will always have degree n. But now we put the values y0 and y1, and the interpolating polynomial is the constant polynomial. Even before you compute the interpolating polynomial, we have two nodes, x0 equal to 1 and x1 equal to 2. And when you have two nodes, the polynomial will have degree less than or equal to 1. If it's a linear polynomial, if it's a line passing through 1, 1 and 2, 1, it has to be the horizontal line y equal to 1. So it has to be the constant polynomial. That much is clear, but indeed our computations also support this intuition. So the interpolating polynomial is indeed a constant polynomial. Although you had only two nodes, the interpolating polynomial is not linear. It represents a line, that is true, but it's not a linear polynomial in the sense that it doesn't have a non-zero x coefficient. It is the constant polynomial y equal to 1. So even though there are 2 points, you may not always get a linear polynomial, and this is why we say that the interpolating polynomial will have degree at most n. This is the thing that we have always been saying. Mathematicians would like to be very precise. Whenever we say that for n plus 1 points we get a degree n polynomial, it would mean that whatever n plus 1 points you get, for all functions you are going to get degree n. But here that doesn't happen, and therefore, to be precise, we will have to say that there is a polynomial given by Lagrange whose degree is at most n. All right. So that raises a question. Could we have got some other polynomial interpolating the same data? Is there a uniqueness? Is there some kind of uniqueness of this interpolating polynomial? That's the question that we would perhaps think about. So how many polynomials can we get to interpolate the given function at n plus 1 points? The question is, you are given n plus 1 nodes, which are distinct n plus 1 points. There is a function taking some values at these n plus 1 points. How many polynomials can you get which interpolates this data? The answer is Many polynomials, in fact, infinitely many polynomials. Why do we get that? This is because Lagrange will give you a polynomial of degree n, at most n, once you have these n plus 1 points. Okay, so you take one more node, you add one more node, n plus 2th node, and make sure that the value of this function that you are going to define on the n plus 2th node is not equal to value of the polynomial that Lagrange has given you. So Lagrange's polynomial now will not work for the new data that you constructed for with n plus 2 nodes. But Lagrange will then say that, okay, since you have modified the data, let me also modify my polynomial. And Lagrange will give you another polynomial. Earlier will not work. So Lagrange will give you another polynomial which will have degree at most n plus 1 now. Once you have this, you can add one more node and make sure that the earlier two polynomials that you had, their values are not the value that you assign to this new node. So you can keep adding nodes, making sure that the earlier polynomials do not satisfy that new value, and therefore at each step you are going to get distinct polynomials. But those polynomials at the first n plus 1 points will give you the data that you started with. So this way there are many polynomials, but their degrees have increased. So the question is, we will modify the question. The question has a horrible answer. The question answer says that, oh, there are infinitely many. Then we will say, okay, let's modify the answer question. Question is, how many polynomials of degree less than or equal to n can we get to interpolate the given function at n plus 1 points? Now there is a unique polynomial. Why is that so? That's because of this very famous theorem from, you may say it's from complex analysis because you are working over real numbers and so on, but this is a theorem which is from algebra, actually, from the part of mathematics by name algebra, where you study polynomials over, what are called fields, and then you will see what are the zeros and so on. So basically, whenever a polynomial has a root, so you have a polynomial px and alpha is a root for px. Then x minus alpha has to be a factor of px. So you will write px as x minus alpha into qx. And then by induction hypothesis, your qx, which has degree less than px by 1, has at most n minus 1 distinct roots by induction. And therefore px will have at most n distinct roots. So a polynomial of degree n will have at most n distinct roots. But when you are saying a polynomial of degree n, that means your x power n has a non-zero coefficient. You cannot have 0 times x minus n plus 1 times x minus x power n minus 1 blah blah blah. That would not be a polynomial of degree n. It will be a polynomial of degree n minus 1. Okay, so whenever you have a polynomial whose degree is n, that means the coefficient for x power n is non-zero, then you have at most n distinct roots, at most n distinct zeros. Now you are given another polynomial which is, say, of degree maximum of n, and if it has n plus 1 zeros, then such a polynomial has to be the zero polynomial. So polynomial of degree less than or equal to 1 with n plus 1 zeros should be the zero polynomial. So now how does that help us in getting the uniqueness for this? Because if there were two polynomials, p and q, and both p and q are of degree less than or equal to n, therefore p minus q is also of degree less equal n. Now p minus q has the property that it gives the value 0 at all these n plus 1 points. Okay, so you are looking at two interpolating polynomials for your data, and important condition is that the degree of both these polynomials is less equal n. Then their difference being of degree less than or equal to n has n plus 1 0, so the difference has to be 0, and therefore both these polynomials have to be the same. This is why we got constant polynomial in the last example, because you are going to get a polynomial of degree less equal 1. And then there is a polynomial of degree 0, which is already doing the job. So the difference of these two will still be of degree less equal 1, but it will be 0 at 2 points. Now you cannot have a linear or a constant polynomial which has 0 at 2 points unless the polynomial itself is the constant 0 polynomial. Okay, so let's just, this is something that is not very important for us theoretically, but this is a very important fact for you to know. Therefore, we have confined only this part only to one slide, but this is something that you should know, that it is important that the degree be less than or equal to n when you are asking for uniqueness of the interpolating polynomial. All right, so I hope you are comfortable with this fact now. Now we are going to study the error. There is bound to be error because you are getting a polynomial, whereas earlier you had some random function giving you the data on those n+1 nodes. So what can be the error? And the formula for the error is very nice, very pleasing formula. But there are some conditions that you are going to need. You will need that your function be n+1 times continuously differentiable. I forgot to mention continuously differentiable. I will put it there. So your function is n+1 times continuously differentiable, and px is the polynomial interpolating your function at distinct n+1 points, x0, x1 up to xn, which are points in AB. Then for each x in this AB, there is some point xi x in the open AB with the property that fx is px plus this error form. How does the error form look like? You may think about this error form to be fx minus px. So the error form, first of all, has x minus x0, x minus x1, blah, 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 x minus xn. They are all there in the error form. Clearly, because whenever you are x equal to xi for any of those xi, the error is 0. So your error form having these as the factor is quite understandable. And if you have some x other than the xi, then the error form has the n+1th derivative of the function at some xi x. That xi x will depend on your x. Okay, so this is the error form, and then there is the n+1 factorial, which is there in the denominator. This error form is very important for us. We are later going to do numerical differentiation, numerical integration, and in that, this error form is going to be used. So the error form is useful. If you remember the error form for the Taylor polynomials, then you may just imagine that these all xi are the same. You know, we have gotten this by assuming that we have distinct points, n+1 distinct points, but let's say that we forget about that n+1 distinct points and all the xi are same. Then here you will have x minus x0 power n, and indeed this, there will be some xi x which will depend on x, and that xi x, you will have some more information that the xi x is now between x and x0. Here all we can say is that it is between these x0, x1, xn. That's the only thing we can say, and x. So if you take the largest subinterval of AB containing x0, x1, x2, xn and x, then your xi x will have to be inside that. That's the only thing we can say, but beyond that we cannot say. But remember that this error form is very, very similar to the error form for the Taylor polynomials. Okay. And yeah, so maybe we can use one of the earlier examples for this 1 upon x, and let's compute the error for the interval 2 to 4. We will see that the error is very, very small. So the error is given by the error form, which is the, remember we have 3 nodes. So 3 nodes means there are 2 plus 1 nodes, and therefore we will have to take the third derivative at xi x. So for every x in the interval 2 to 4, there is a xi x in the same interval such that the error fx minus px is this particular quantity. Okay, and we want to compute, suppose, so we can also write down the error form completely. We have fx equal to 1 upon x, which is x inverse. Its derivative is minus x power minus 2. Second derivative is 2 times x power minus 3. Now there is no minus sign, but the next derivative will again have a minus sign, which is minus 6 times x power minus 4. And suppose we want to find the maximum possible error that we can have. And let's also say that we want to find the maximum possible absolute value. Okay, so the error form is indeed this. This 6 has been cancelled with the denominator 3 factorial. And so we have minus of xi x power minus 4 into the product of these 3 degree 1 polynomials. This is our error form, and we want to compute the maximum possible value of this. So to find the maximum possible error, it's a product of two forms really. One is this xi x power minus 4. Since you're taking absolute value, you can forget the minus sign which is there outside. So it's this part, xi x power minus 4 into the other part. And we will compute the maximum for both of them. So xi x power minus 4, the maximum value of this is going to be achieved on the point x equal to 2, and it is 2 power minus 4, which is 1 by 16. So the only thing that is now remaining is the product of these 3 points, x minus 2, x minus 2.75, x minus 4. So let's call that polynomial to be gx. Okay, we call it here qx, x minus 2, x minus 2.75, x minus 4. To find the maximum value of the polynomial, we have to find the critical points. For that, we need to find the derivative. Derivative is 3x squared minus 17.5x plus 24.5. If you write it down as rationals, you will have 3x squared minus 35 by 2x plus 49 by 2. Okay, and you can also divide by the 3 alongside and take the 3 common. That way you will be able to write down the zeros, and you will see that the zeros are indeed 7 by 3 and 7 by 2. You can check that the sum of these two is indeed 17.5 upon 3, and the product is this upon 3. So product is 49 by 6 and the sum is 35 by 6. So we also compute the values of those at those points 7 by 3 and 7 by 2 of our polynomial q. So at 7 by 3 it is 25 by 108, which is roughly 1/4, whereas at 7 by 2 it is roughly half, forgetting the sign. So the maximum is achieved at 7 by 2 and possibly also at the endpoints of the interval 2 and 4, but there the values are 0. Okay, so the polynomial qx, the values, the maximum value is to be computed by computing the critical points, compute those values and compare also the points at the end, the border points, the end points, take their values also. And at q takes value 0, at 2 and 4, so those are to be ignored, and therefore the maximum value is 9 by 16 under modulus. Therefore, the maximum absolute value of the error is less than or equal to the 1.16 which you got from here, xi x power minus 4, and 9 by 16 which you got as the value at 7 by 2. And therefore, the product is 9 upon 256, which is roughly 0.0351565. Not roughly, it is equal to that number. Okay, so we will see one more example of how this error form can be used to write down a function very nicely using the Lagrange interpolating polynomials. And then we will see some more ways to compute these Lagrange polynomials in our next lecture. So thank you and see you then.